my pleasure to welcome you all today at the CIBM Breakfast Science, which is held here at PCI EPFL. And today I have the pleasure to introduce Omar. So Omar is working with us. He's a postdoctoral researcher, and he's working with us since 1 year now. 1 year.
1 year, 2 months.
2 months. Ooh, yeah. 3 months. Ooh. And so Omar is working with us since 1 year and 3 months. He's supervised by Bernard, and he's working jointly with in an Inno-Swiss project with Volumina. And he is mainly working on PET-MR and abdominal MR and PET-MR, of course. So he is implementing now here the PET-MR part. As you know, we've upgraded our 9.4 1 year and 2 months more or less with an PET-MR system. So it's a job of Omar to make it run. And I think that he's doing quite a good job for that. And he will be presenting a little bit on it today. And a little bit of the journey of Omar. So Omar had his PhD in France, University of Orléans, and he works mainly on multimodal imaging and image processing for jointly joining together different modalities like MR and PET, as you see here, and also CT scans and also some ultrasound, what he did as a postdoctoral researcher in Paris at the Cardiovascular Center, if I remember correctly. So I guess that this is mainly all about Omar. It's already a lot. And Omar, thank you for accepting to give the talk, and have fun.
Okay, thanks to you, Cristina. Well, thank you everyone for coming. My name is Omar Zenteno, and the topic of my talk today is my work during this year and 3 months that I have been here. The title of my talk is Multimodal Approaches to Preclinical Abdominal Imaging, Dixon-based fat water separation, and PET MRI integration. So my presentation is going to follow a simple structure. Well, I was going to talk about me, but Cristina already gave a lot of detail. I will talk about the project and the motivation, the problem, the 2 different approaches that we took. First, the MRI approach, secondly, the PET approach, and then the future perspectives on how we are going to mix both approaches into a single multimodal pipeline. Of course, we end up with the conclusions. So this is my scientific history. Basically, I worked first in Peru at PUCP, the University of Orléans, and INSER, where I had different projects. Cristina already talked about them. I have been working always with multimodal imaging. So my work is to use 2 different modalities and extract information or generate new information that is not possible to obtain without the combination of both modalities. Then I arrived here at EPFL as a postdoc, as part of the Inno-Swiss project 113-704. I work in collaboration with Bernard, with Constance, and also with Doreen. The project is focused on monitoring subcutaneous implants in vivo, like the ones that you can see here in the upper part. They are usually implanted in the dorsal and in the ventral part of the rats. Now, our part in the project was to perform the experimental validation in the animal model, and also make the follow-up of this in both modalities, MRI and PET. So we had a problem. We had a beautiful pipeline where we usually inject the biomaterial in the rat. And then we have a window of 6 months where we are going to make an evaluation of how the implant grows over time. And finally, the animal is sacrificed by our collaborators. And then they will do analysis in terms of histology and also flow cytometry and different parameters that we will try to correlate with what we have obtained in this initial window. And it has 2 significant challenges. First, that the traditional measurements are calipers. And calipers, they are prone to interoperator variability. So we decided also to apply some computer vision techniques in which we made photogrammetric reconstruction using different photos that were respiratory gated. But this has exactly the same limitation. They both fail to show how implants develop over time beneath the skin. So then the immediate answer was to use a T2-weighted MRI imaging pipeline. So in this specific pipeline, that has been implemented before us. They were able to make a segmentation of these implants using T2-weighted sequence. And the results were really encouraging. They used a specific 3D unit network to make the segmentation. However, they did not extend this to the field of the metabolic imaging. And that's what we are going to do now, to add a second layer to this MRI information that contains also metabolic information. So we have the same pipeline, and in this specific window of 6 months, we are going to do analysis in the MRI context, and also to evaluate the tissue regeneration kinetics by using PET. So we have these two specific objectives. Now, thankfully, we had this new PET insert that was acquired in our laboratory, and that was compatible with the 9.4 Tesla MRI that we had also here. So we were able to do both modalities simultaneously. We decided to go first through MRI independently, and then through PET independently, and then make the combination of both of them. So let's begin with the MRI approach and how to make an automated implant segmentation using a specific protocol that is turbo-rare Dixon MRI. If we just go through a T2-weighted MRI image, we will see that we have not a perfect delineation of the borders of implants, and also we have a superposition of the skin over the implant. This is because of the chemical shift that is produced by the presence of lipids in the area of scan. So we also had into consideration that our implants, they contain both water and lipids. So the initial approach that we decided to take was to use Dixon MRIs that takes acquisitions with 2 different echo times. So then we have an acquisition in phase and acquisition out phase. And with this, we can generate an image that contains only the water component, and also another one that generates only the fat component. So you can see in the 2 images below. So the water component image allows us to have a good delineation of the borders and also a higher contrast compared to what we had before. And the fat only reconstruction allows us also to have a delineation, but it's more like in the negative space. So then we decided to go forward with the Dixon water only reconstruction as the main source for our segmentation. We will see later that we made a mistake there, and the fat only reconstruction can also provide some information. This is not the only outcome that we can obtain with this. By the combination of both reconstructions, we can also generate a new watt-father composite that corrects the chemical shift. And as you can see in the image on the upper right, we have a better delineation of the implants. Also, the skin is exactly in the position where it should be next to the implant, and also the contrast relation between the implant and the rest of the tissue is higher. And it allows us to have a more robust, reproducible, and active-free contrast for longitudinal implant evaluation. In terms of how we divided our cohort and our first experimental strategy, we had 4 rats that they were implanted with 8 implants, 4 in the dorsal area and 4 in the ventral area, for a total of 32 different implants. And in terms of the acquisition time, we had 5 time points, 1 for day 1, day 7, day 14, day 21, day 28, and day 60. The initial results were obtained with a manual segmentation. As you can see on the image on the left, we did a manual segmentation, which is labeled in red here. For each of the implants, the acquisition sequence was a Dixon turbo-rare with a repetition time of 3,000 milliseconds and an echo time of 20 milliseconds. We had a 0.21 times 0.21 millimeter implant resolution, also a typical slide thickness of 1.25, and the overall field of view that we were covering was 70 times 70 times 60 millimeters. The initial results that we obtained with the manual segmentation were really encouraging, especially because we didn't find much variability in terms of how much the normalized swelling rate changed over the different time points of analysis. And specifically, we were really happy with this because we had 7 different types of implants, and one of them, D, was particularly special for us because it was a control implant. So it was not going to change in terms of volume over all the longitudinal study. When we evaluated this implant with the manual segmentation, we saw that over all the longitudinal study, it kept a ratio of 1. Why this is important? Because with this, we can prove that the manual segmentation that we are doing really represents the volume that we are observing inside the animals. And when we compare this to what we obtain with a caliper measurement, the difference is obvious. There is more variability in terms of how much volume we estimated for each of the implants. And also it's clear that the intervention of different persons taking the same acquisition has a big effect into how variable these results are. Sorry. However, the manual segmentation takes a lot of time. Usually to do one rat, it takes 1 day to do each of the implants and then go through all the segmentations again and refine them and everything. So we recruited a master student, Ali El-Bindari. He made really good work using the data that we had. At that moment, we only had the time points that I presented before, that created a data set of 1,072 water component slices, 1,072 fat component slices, and an equal number of masks of ground truth. So the objective of his project was to use these ground truth segmentations that we did previously manually and use a fine-tuned SAM model. SAM model is a segment anything model from from Meta. And he generated a predicted coarse mask that was just classifying the image in 2 classes, either implant or not implant. His results were really impressive. Actually, he got a Pearson coefficient of 0.917 in terms of the predicted volumes and the ground truth volumes that we had from the manual segmentation. But more important, visually, as you can see on the right, we can see on blue the blobs that he generated in 3D by making a concatenation of each of the segmentations that he made on 2D. And when compared to the original manual segmentation that we label as ground truth, the root mean square error in terms of volume was less than 7% of the average volume. Let's have into consideration that all these numbers are taking all the implants as a single class, and that's why the volumes are this high. So with this, we were able to say that SAM, it's a model that can allow us to have an accurate and a reproducible volume estimates without minimal deviation from the manual reference. And we can see that also here in a complete overlay of the segmentation over a corresponding image without the segmentation, where we can see that the implants, they can also, the segmentation also embrace the shape of each of the implants and it allows us to access to them independently. How we do this? We can check the neighborhood of each of the implants, and based on how many pixels are close to the neighborhood of each of the implants, we can separate them and make an implant-wise analysis. These are some results that we obtained from a different time point that was not exactly on the data set of Ali. And since we saw that at the 5th time point we had a plateau, we were expecting also to have not much development between the 2nd month and the 3rd month. And the results were really coherent with this, with normally 5 or maximum 20% of increase between one of the other, between month 2 and month 3. However, we saw that there was not consistent behavior for some implants. And the reason for this was that some of them had different constitution as when the time passed, they start changing in terms of the constitution. So for example, what you can see here is an implant that has homogeneous contrast, But when it's compared to the one that is here, this has like a crown effect that is surrounding the center of the implant, which make us believe that there is some degradation of the initial material. And the same can be observed in the implant here, but in a less homogeneous distribution. And this is common also in the mixed image. So I would like to make an emphasis in the fat image, in the fat component image, that so far we didn't pay attention to it. And I don't know if you can see this, but they have something in common for all the three implants, that they are perfectly delineated in the fat image, as you can see on the borders that are highlighted here, independently of the composition that they have on the other component. So this led us to believe that the fat component also had some value to improve the initial segmentation that we have performed over the other component image. So what Ali proposed also as the last part of his thesis was to add the fat MRI scan as part of a second level model that was a fine-tuned self-refiner model. It's basically a UNet, and it allows us to provide refined mask over the masks that were generated with the initial SAM model. He made some preliminary results to evaluate how these dice values change when they added this extra step in the model pipeline. And we observed that from an average of 40%, dice went to values higher than 80%, which is a significant increase. And also, it's really encouraging as an early result to say that the fat component will also add value to the segmentation that we have performed. So as a summary, in terms of what we did with our MRI approach, we worked with a fine-tuned SAM model, and the average dice was of 85.8%. The segmentations, they were really coherent with what we can observe on the water component images. As you can see on the image on the right, the labels are colored as blue. The volumetric analysis also shows an average relative volumetric error of only 2.61%, which is really low. And we had a successful integration of the model within the 3D slicer interface, because he made also an interface that allows us to connect the results that we will have here with what we will obtain later on our PET approach. Finally, SegRefiner shows a really strong potential for segmentation refinement, as definitely something that we are going to explore now that we have more data, and now that we are using also the insert to make also the MRI images. So all the results that we obtained with MRI are going to be complemented with PET. And what is the value of PET for this specific pipeline? That they are going to bring metabolic implant characterization. I will just go back a little bit to remember that we have the PET inserts. These PET inserts are geometrically, well, they are inserted into the 9.4 Tesla MRI, and they are geometrically aligned, so they have an inherent transformation function that allows us to have the initial registry. However, we did the initial exams with the calibration phantom. We observed that even after doing a calibration, there was some misalignment between what we can see as a PET image in yellow and a gray image, which is the MRI. This image were obtained from this specific phantom, where we have 3 different axes that cross to each other. It's in a background of water, and in the internal part, we inject FDG. So ideally, what we should have here is a complete superposition of both of the crosses that we see on the video, and it's not what we were obtaining. So to improve this, we modded an SPM12 package in MATLAB, and we use a normalized cross-correlation metric to make a registration, which will allow us to have a lesser degree of error in terms of how we register R1 to each other. The colors in the project don't help much, but you can see here that there is a red line here corresponding to the MRI that is not present here when we are doing the proper correction for the co-registration. In fact, in this area, we can see this at a level of orange, whereas here we can see a clear separation between red and green, which represent MRI and PET. And in this case, we also see there is a deviation from the registration in these borders. And when we apply the correction, we remove this false overlap that we had in this specific data. When we approach these results numerically, we can observe that before we had a normalized cross correlation of 0.79 in average, and with the correction that we performed, it went up to 0.86. This was translated into Euclidean units to a displacement of 0.44, which it seems a bit low, but it's significant in terms of the relative size of this compared to the size of the targets that we have inside of the rats. So after we make this correction, then we said, okay, let's try to add this metabolic information to the images that we already have and make also a relation between the metabolic data that we'll obtain and the labeling of the implants that have described the geometry in the previous results. This is a conceptual illustration of what we want to do. We want to have the PET on top of what we have segmented from the MRI. And this will be really useful because it will allow us to have also a trace of the kinematic parameters and also make a proper quantification of the metabolic activity in these specific areas and only on these specific areas. But to be able to do this, one of the first steps that we need to do is to obtain an input function. And in this case, we follow the works that were previously presented by Bernard and also from Borghesi that make use of the activity curves that we obtain from the vena cava. As you can see, this is a video of dynamic reconstruction of PET that shows how the FDG is dispersing after the injection inside the vena cava. And we made a segmentation of the central part of this area and also generated input function curves that represented the activity over the units of time in this specific point of analysis. What is important from this function is that it allows us to have a clear differentiation between the initial injection of the tracer and also an initial injection of the bolus, the chain that pushes the tracer inside the subject. So in general terms, in terms of what we did on the PET pipeline, we were able to make sequences that allow us to make dynamic reconstructions with different time intervals. These sequences are corrected also with the information from MRI in terms of movement and also in terms of motion control. And we are able to have specific regions of interest that are correlated to what we have on the MRI images just by applying the same mask of segmentation after we have the transformation matrix that was corrected with the initial calibration phantom. So now we have a pipeline that is oriented to PET and a pipeline that is oriented to MRI. What are we going to do next? Now we have just get a new cohort in which we will use to scan with the PET insert using the coil that corresponds to it and also the gradient that was installed in the 9.4 test. So with this specific configuration, I will be able to generate the illustrations that overlap the PET images on top of the MRI evals for specifically each pixel that corresponds to the geometry of the MRI segmentation. But this will not only stop that. The objective is also to combine this with what the other collaborators from our lab are working on. And the immediate approach will be to apply the transformations that we have for the atlas of the brain, and then use this same template to transform the estimates that we will obtain on PET on the brain and compare it with the metabolic values that my colleagues obtained here with MRS and also with the different techniques that they have implemented. Specifically, the first approach will be to correlate FDG uptake with CMRR glucose measurements. This pipeline will enable direct comparison between FDG uptake and this specific metric CMRR glucose in vivo. So as a conclusion, I would like to highlight that with the specific structural characterization using Dixon MRI, we were able to make a complete localization of the implants on the MRI images and also have a complete description of the geometry of them. We implemented the AI-based approach that allows us to do this faster and not take days to make the segmentation. And also, we're implementing the PET pipeline in order to have the activity curves that will allow us to have comportamental analysis done prior the segmentation that we do on the MRI. In general, the message that I would like you guys to take home today is that the PET MRI will allow us not only to see the implants, but also to quantify the metabolic activity and how this is progressing over all the longitudinal analysis. Thank you so much for your attention.